Bismillahirrahmanirrahim. Today, inshallah, we shall talk about triangles and a concept called coordinate proofs. You can talk about triangles purely in a geometric sense, using geometric theorems, definitions, and properties, etc. Or you can place triangles in the coordinate plane like I have drawn over here. And you can use the coordinate plane to prove geometric concepts. Here I have, for example, a triangle that's outside, that's drawn without the coordinate plane, and you can use geometry to prove certain concept. For example, if I was given this isosceles triangle and I was told that this particular point is the midpoint, for example, then I have these two smaller segments to be congruent, then I can prove these two triangles, the baby triangles, to be congruent by side, and I can prove these two angles, for example, to be congruent by CPCTC. Now, we can do a lot like that without using the coordinate plane or the Cartesian plane. On the other hand, we can also do a lot by using the Cartesian plane and kind of bridging the gap between geometry and algebra, so to speak. For example, I've drawn here a triangle superimposed on the Cartesian plane. And when we put a geometric figure in a Cartesian plane, of course, we can assign each of the vertices a ordered pair that belongs to the place of that particular vertex. And when you're placing geometric figures in the Cartesian plane, it is beneficial for us at least to put one of the vertex, like over here, x over here, this is a capital X over here, on the origin itself, because it gives us the ordered pair 0, 0, which makes our life much easy. So when we place geometric figures in the Cartesian plane, we like to put one of the vertices in the at the origin, which helps us in doing our work. You don't have to, but it is oftentimes very helpful. And you can do it in a similar way. You can assign each vertex in a particular ordered pair. So if this is 0, 0, and if this was A, and then the y here has to be 0 because it's on the x-axis. And this particular ordered pair over here, you could call it any particular ordered pair. You can call it like B and C, for example. If it happens to be a midpoint in the middle of this right here, then it would be half of A, wouldn't it? Because if y is this point here is the midpoint between these two, it would be half of A and some value over here that's like that B. So you can place geometric figures, or in our particular case here, triangles, in the Cartesian plane and assign ordered pairs to proper ordered pairs to each of the vertex, and we can use algebra. We can use algebra to prove mathematical concepts, mathematical theorems, or whatever else that is of our interest. So using coordinate plane, we can actually prove many geometric concepts, and that's what we shall talk about today. Here's a great question, for example, that does precisely that. That is, it uses the algebra and the coordinate plane to prove a very interesting theorem, which we shall in fact encounter in the future. So let's look at this particular question. It's a very beautiful question, and work through it. So here we are given triangle ABC. So here's triangle A and B and C. Those are the three vertices of this triangle. So and here the ordered pair belongs to A is not written, so I'm going to write it down. That's the origin 0, 0. So that's a triangle that's drawn in the Cartesian or the coordinate plane. So we're given that it is a triangle. And then we're told that S is the midpoint of AC. That is, that segment is congruent to that little segment there, okay, as being the midpoint. Got it. And then we're also told that T is the midpoint of BC. Now that means that this is congruent to this, like that. All right, so that's the given information. Now we're asked to prove that ST is parallel to AB. We are asked to prove that this ST is parallel. So we're asked to prove that ST is parallel to AB. Now, if this was a geometry problem, the way we would do, if this is a purely geometry problem without the Cartesian plane, we would have a triangle like this, and we have a segment like this, and we are told that those were midpoints like that, and we would be asked to prove that these two are parallel. Well, the way we would try to go about doing that is to show two lines to be parallel, we have to go back to our two lines that are cut by transversal, such that the corresponding angles are congruent, then the lines are parallel, or alternate interior angles being congruent and alternate exterior being congruent, or the consecutive interior angles adding up to 180 degrees. If we could do that, then we would prove those two segments or two lines to be parallel. So if this was purely a geometry problem without the benefit of a Cartesian plane, we would try to, for example, make these two angles, prove somehow those two angles to be congruent, and we could prove those segments to be parallel from a corresponding angle postulate converse, right? So, but that's not what it is over here, and that'll be kind of tricky to do anyways. So what are we going to do over here? So now this will also show you the beauty of this particular method, that is using coordinate plane to prove geometric concepts, or doing what's called coordinate proofs. So now let's look at this question again. So if we're given this triangle and we're given two midpoints S and T, which implies those two segments are congruent as I've drawn over here, and we're asked to prove that these two segments or lines are parallel. Well, the first thing to appreciate is if two lines are parallel, or two segments are parallel, then they have the same slope, right? They have the same slope, or they have the same m. So if we can prove that these two segments have the same slope, then we are done, right? Because that's what it means to be parallel. I got it. Now, the other thing is there's a lot of other information that's given to us that's in the diagram. We're given the ordered pair that belongs to each particular vertex. A is 0, 0, because at the origin. So that's the ordered pair that belongs to A. Here we're given that B is this ordered pair, 2A and 0, A being some number, okay? And we're also given B, which is 2B and 2C. Now, why did they choose those particular funky-looking ordered pair is something of interest, but that's what they did. And there's some insight into that, which is basically to make the math easy for us. So they're doing us a favor by actually giving us the ordered pair. Now, if they did not give us these ordered pair, you actually could come up with your own ordered pair. You could call this one AB, and you could call this one, PR or something like that, and work with that, and that you should still come up with the same math actually. So anyways, they gave us these particular ordered pair for A, B, and C. A is again 0, 0, and the B is 2A and 0. Notice the y coordinate is 0 because it's on the x-axis. This point is, and we're given C to be 2B and 2C. So those are the ordered pair that's given to us. And then we are asked to again prove that these two segments are parallel. Well, to prove those two segments parallel, our working plan is to prove that they have the same slope. Okay, so if we can prove that they have the same slope, if ST and AB have the same slope, then we're done. Now, and then the other interesting thing is you have to understand the slope of AB. Well, what's the slope of AB? Well, the slope of AB is 0, isn't it? It's a horizontal line. So slope is AB. So if you can prove that the slope of ST is also 0, then we're done. But okay, anyways, let's go about it. How do you find the slope? So let's call it like step 1. We can call step 1. So our step 1 here goes to find slope. So we're going to find slope. This is our plan. Find m, find the slope of ST, segment ST. That's what we're going to try to do. Well, to find the slope of ST, we have a formula. Slope is a change in y over change in x. In other words, that's y2 minus y1 over x2 minus x1, if you recall. That's change in y over change in x. In order to do that, we have to have ordered pair that belongs to S and T. How do we do that? Well, we need the ordered pair for S, and we need the ordered pair for T over here. So how are we going to find the ordered pair? Well, S is the midpoint of A and C, isn't it? So S is the midpoint of A and C, and if you recall the midpoint, there's a formula for S, basically average, right? The formula for finding the midpoint is the average of the axis, x1 plus x2 divided by 2, and y1 plus y2 divided by 2. That'll give you the midpoints. In other words, you just have to take the average of the ordered pairs to get the midpoint. Okay, so we're going to find the ordered pair for S. Well, it's going to be the average of A and C. That's going to be 2B, that's this, plus 0 divided by 2, and then the y coordinate is going to be 2c plus 0 divided by 2. That's easy peasy. Now you can see how the math makes it easy, right? So this is going to be like, this is just 2b over 2, and this is 2c over 2, like this, right? And if you simplify this, s is just going to be b and c. Ha! That works out very nicely. So this ordered pair is in fact just b and c. In a similar way, we can find the ordered pair for t. Okay, so let's find the ordered pair that belongs to t. So t here is going to be simply, again, the average of the two. So I'm just going to write 2b plus 2a. That's this plus this, 2b plus 2a, and divided by 2, and 2c plus 0. That's the y coordinate. 2c plus 0 divided by 2. And if you simplify this, you get, and you can factor out a 2 from here. You can simplify that and divide that. So you get, basically here you get b plus a, right? And c. That's what you get. See, if I went too, whoa, what did you just do? Okay, I went too fast, right? I'm going to simplify this, okay? So watch. 2b plus 2a divided by 2. Okay, so first thing you have to do is you have to factor out a 2. You can't just willy-nilly cancel out stuff. So you factor out a 2, you get 2b like that, and then you divide them out, and you get b plus a, and that's what I've written over there. So if you simplify that x coordinate, you get b plus a, right? So all right, we got that. So, or a plus b. So we got t. So we have t over here. I can write b plus a, or I can just write a plus b, right? So I'll just write b plus a, and then c over here. So we got that. So now we have ordered pair belonging to t and s. So now we can find the slope, right? So it's change in y over change in x. Okay, so we can find the slope of st. So finding the slope of st, which is like our step 1, is going to be y2 minus y1. So it's c. That's y2 and y1. So it's c, and they happen to be c. Change, and then x, and then x minus x2 minus x1. That's b plus a. That's over here, and minus b. Okay, so while c minus c is 0 over, well, this happens to be a, but that doesn't really matter because anything divided by 0 is 0. Ta-da! We did it. So the slope of st is that. And then step 2, we're going to have to find slope for AB. And we kind of know it to be 0 because it's a horizontal line, but let's do it. So the slope is y2, just changing y over changing x. Let me just write it down. And using this, so it's 2 changing y. Be careful, I made a mistake. So 0 minus 0 over changing x, which is 2a minus 0. And that's 0 over 2a, and that's still 0. So the slope here is 0. So as you can see, the slope for both of them is so is the slope for st equals to, let's not put a measure of st. So the slope of st is equal to the slope of AB, and they're both 0. Since they have the same slope, st is parallel to AB. Ta-da! And that's how we do this. So the beauty of this is, in fact, this is a very, now if you thought this was complicated, you might want to do this question again until you like zippity do that. You can go do it in your mind, because it's not too complicated. It looks complicated, but it's worth getting to know this phenomena. So what we did, this proof is actually not very difficult, and geometrically this would be kind of tricky to prove, but what we did here is rather beautiful. We took a figure that was in the Cartesian plane, and there's some assigned ordered pairs to each of these. You could have named them anything. The math would always work out the same. This both of them slope will end up being 0. You could name them A, B, C, D, P, Q, R, S, whatever, and the slope will still end up being 0 by mathematical calculation. So we took a geometric figure, we placed it in the coordinate plane, and we assigned each vertex an ordered pair, and we found the slope of each particular segment, but first finding out the ordered pair for S and T, and we proved that the slope is the same and the lines were parallel. Now this is what's called a coordinate proof. taking geometric figure and placing it in the ordered pair and proving a geometric concept, in fact. So and that's the beauty of these proofs, and they are there's a perfect cooperation between geometry and algebra, and I really enjoy these. Okay, let's see what we have next. Okay, so here we go. So this is actually a very beautiful question, and I had not seen this before today, and I found this question to be quite intriguingly excellent. So here's the question. The question says basically to write a coordinate proof to prove the triangle ABX, that's ABX, X is right here. So we are asked to prove that this particular triangle is congruent to CDX, to this triangle. So we are asked to prove that those two baby triangles over there are congruent. So that's what we are asked to prove. I'm sorry. So, and then we give an ordered pair that belongs to each of these vertices. So we get AA is at the origin, and B is 0 plus X plus B, and C is A plus X and B, and D is A and 0. So we're given a whole bunch of, and then we're given X, and X is like A plus X over 2 and B over 2. There are several ways of doing this, and I don't know how the questioners intended us to do. But again, our goal here is to prove that this triangle is congruent to this triangle. Well, there are only so many ways we can prove triangles to be congruent, right? So there's side, 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 angle, side, angle, side, angle. There's angle, angle, side. And there's hypotenuse, leg. That's for right triangles, right? So we can use any of these 4 ways to try to prove that these two triangles are congruent. So, but the question is, which one of these methods are we going to be using these two triangles to be congruent? And there's more than one correct way of doing this question. We can use side, 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 angle, side, angle, side, angle, and angle, angle, side. These are the 4 ways that we can use in this particular case. Now, so which one do we use? If we wanted to prove using side, 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 then we have to prove that this segment is congruent to this segment, and then this segment is congruent to this segment, and this segment is congruent to that segment. We would have to find the length of each one of those segments, and that's kind of like tricky to do. And that's going to be a lot of math. It's going to be busy work, okay? Just because you have to use the distance formula. If you remember the distance formula, it's square root of changing x squared and changing y squared, like this. Okay, so you have to use the distance formula to find all those little distances. Okay, that could be tricky. Okay, so I'm going to say I'm not going to use this for now. Side, angle, side. So we have to know the rest of them. If you understand, they need at least one angle in there. So we have to find one angle that's congruent between these two triangles. You see it? Well, I hope you do, because there's vertical angles right there, and they're congruent. Okay, so we got our vertical angles. So we got one angle. All right, if we were to prove these two triangles to be using side, angle, side, we would have to prove that this is congruent to this, and that is congruent to that. That's what we're going to have to do, because it's A, B, C. Okay, you have to be careful. ABX, so ABX to C, DX. So the corresponding sides are these, as I have labeled. So if we wanted to use side, angle, side, we would have to prove those two segments to be congruent. Okay, wow, that's very interesting, because if we draw that out, it would imply that X is like the midpoint of BD, and it would imply that X is also the midpoint of AC. That is, if we could prove that X is the midpoint of these two segments, then we have the congruent sides, and we're done, right? And you can use side, angle, side to prove those two congruent. Okay, that might actually work. So, but I just have to prove that X is the midpoint. Well, we're given what X is, so if we can prove that you get the same thing by using AC, that is, if you find the midpoint of AC, it ends up being this, and if you find the midpoint of BD, it ends up being that, then we've proven that X is the midpoint of both of them, and then we know those segments are congruent. We don't have to do all this distance formula math. Well, how do you find midpoint? So let's find the midpoint. So let's find the midpoint. Okay, let's find the midpoint of AC, segment AC. Well, the way we do that, we just average the x's and average the y's, right? So let's find the average of the x's. A plus x, that's this over here, okay, plus 0, aha, that works out, divide by 2, okay, that's the x part, and the average of the y, that's b over here, okay, for AC, right? So b and y is conveniently 0, so I love that because a is at the origin, right? So divided by 2. So the midpoint of AC is simply a plus x over 2 and b over 2. A plus x over 2 and b, ta-da! So we know that in fact, therefore, x is the midpoint, Okay, so we established that x is the midpoint of AC. Okay, so that's very important. We established that x is the midpoint. Can we get lucky maybe and find that x is also the midpoint of BD? Well, let's find out. Let's find the midpoint, okay, of segment BD. Okay, to do that, we again do the average of the x's. So start with here. So we take the 0 plus x, that's the b, and then what's the x over here? Oh, that's a right here. Average of the x's plus a divided by 2, and average of the y's, in this case, is b plus 0 divided by 2. Again, the midpoint formula is this. The midpoint, okay, is simply the average of the x's, x1 plus x2 over 2, and y1 plus y2 over 2. That's the midpoint formula. And if you do that here, if you simplify this, you get 0 plus x is 0. So you get like, okay, x plus a here. If you simplify this, you get x plus a, or a plus x, same thing, right? Over 2 and b over 2. And as a plus x over 2b over 2. And that's again the same thing. So therefore, so from here, therefore, x is the midpoint of BD, segment BD. So what we've done here is we proved that x is the midpoint of both of these segments, and then we can say, since it's the midpoint, okay, so since it's the coordinate proof, so we can kind of go like, I need a little bit more space here, okay, so here, so now so if we're writing this proof, okay, so then we can say that bx, okay, is congruent to dx by definition of midpoint. Okay, and then we can also say, this is like a paragraph proof, so bx is congruent to dx, and we can also say ax is congruent, that's this segment over here, is congruent to cx, that's also from the definition of midpoint. And then we can say this angle bxa, that's this angle over here, angle BXA, maybe I'll use that color so we can kind of keep the angles together. So I can say angle BXA is congruent to angle CXD, those two, okay, because of vertical angles are congruent, okay, there. So now we have everything that we need to make our big claim, and that is, therefore, triangle ABX is congruent to triangle CDX because of side triangle congruence postulate. Ta-da! And there we have it. So this is a very beautiful example where you can use algebra to prove a geometry problem. So we had given a certain ordered pairs for each of them. We proved that the x was the midpoint, and then from there we got congruent segments from the geometry that we knew, and then we proved triangles to be congruent. All right. So when I first tried to do this question, actually, I had a slightly different approach, which is just very interesting. So let me try to suggest to you what I was thinking first. Now, here's the original question. I said, well, how are we going to prove these triangles to be congruent, right? So I knew the vertical angle. Right? Vertical angle is like a gift from God. You know, alhamdulillah. You know, it's like you can use them. So if you wanted to prove them to be congruent, you can use side angle side. But So here's, we said side, 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 angle, side, angle, side, angle, 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 side. I said to myself, okay, well, maybe I can do it some other way. Maybe I could use angle, angle, side. Well, to use angle, angle, side, I have to get some other angle. I have to get another angle. And I thought I could get this angle to be congruent to that angle, right? How can I do that? Well, first I have to prove that these two lines are parallel, and that's actually easy to do. If you find the slope of these, then you using this, because you have ordered pair, it ends up being quite easy. Then they have the same slope, and then you have those two angles to be congruent. So, and then you can find, and then you need a side. You have to prove a side, angle, angle, and you can prove this to be congruent to this. You can use the distance formula to do that. And in fact, math works out to be quite easy because the x's cancel. So you can use different methods of doing the problem. There's more than one correct and more than one beautiful way of doing these questions. So today we talked about triangles and the coordinate proofs. You can do a lot of elegant proofs with any geometric figures. In fact, placing them in the coordinate plane like this. And in these questions, we were given the vertices and the ordered pair that belong to vertices. In many times, more challenging questions will ask us to name those vertices ourselves, and they work out just the same. I hope you enjoyed. Until next time, as-salatu was-salamu ala rasulillah walhamdulillahi rabbil alameen. Assalamu alaikum.